Still not. You can't buy me
Okay. Why would I buy you any of these things?
May I have your attention, please?
Because you love me, right?
We're going to continue with this. We started yesterday. Oops, I haven't changed over. This. We had just started the PCL5. In fact, I don't think we got to this yesterday, did we? No. Coordination number 5. We finished with 4. PCL5 is a structure that looks like this. The phosphorus is in the middle. You don't have much of a choice here. You have to put a Cl on 5 different sides of the P, like that, and then all the Cls have the lone pairs on them. I shouldn't have started. Yeah, that's good. Notice that the P has 5 bonds on it. It's got 10 electrons. That's okay. If an atom is big enough, it can have more than 8 electrons around it, its valence shell. Do you remember what I said was big enough?
Okay.
What does it take? What atoms are big enough to allow more than 8 electrons around them? Yeah, third row or bigger. Right, which phosphorus and sulfur are in. So if you have a third row or bigger central atom, then if you need more than 8 electrons around it, it can happen. Farouk?
So like arsenic would be an element that could have 5.
Yes, yes it could. Yep, and sometimes it does. So what is the shape of this thing? Now we need to spread out 5 orbitals as far apart as they can get from one another. That's what Vesper theory says. And the shape of it winds up like this. You have 2 chlorines that are one's up above and one's down below. So they're in a line, all 3 of them. And then 3 of them are in the plane that's perpendicular to that line. Like that. I would think of it 3 along the waistline there of the phosphorus. Where one's on top, one's on the bottom. What would this shape be called?
Trigonal
Couch potato.
No, it's one of those heat
That's very good, Jessica.
What wrong?
Did you say trigonal bipyramid?
A trigonal bipyramid, this thing is called. You've got a pyramid up above that plane and a pyramid down below the plane that's upside down. A trigonal bipyramid. Jessica, how'd you know it? You what?
I studied.
You studied. Nice.
Jessica!
Nice. Study partner.
No, where?
She's got it. She's got this. So the name of the shape on this one is trigonal bipyramid.
Yeah, I swear.
And what is the bond angle? Are they all the same bond angle? In this?
No.
I don't think they are.
You have some squeeze and some.
Remember that some of these are perpendicular to others. So some of these are 90 degrees, but what about others?
120.
Yeah, so the angle of the trigonal bipyramid is some are 90 and some are 120.
It's 5.
Right. Very much so.
I know.
So yeah, there's our bond angle is 90 and 120. Okay. So when your coordination number is 5, you've got to spread 5 as far apart from each other as they'll go. And so the best data that we have says that it's going to make this shape. The next compound, and by the way, I do have a model of PCl5. There it is. So you can kind of get the sense there that you've got 1 above, 1 below, and then 3 along the waistline there, drawn like the trigonal bipyramid. The TeCl4 is the next one. Would you take a moment and try to do the dot structure for TeCl4? Te, most of us don't even know where Te is in the periodic table. It's tellurium in the oxygen family. In the oxygen family. Next to iodine.
Next to iodine.
Oh, for me it looked like it was next to like R and U.
Yeah, that's TC. That looks like an E too. It's very cold.
See, now you know that picture. And I'm gonna get new glasses. So
Good idea. I want your eyes to fail you just when you need them most.
oh, on the AP test, right?
Yeah. see something strange about that dot structure? What? Yeah, you need to add another lone pair where it doesn't look like there belongs one. Right? Not bipolar, bipyramid. Okay, so I don't want to make it look like I'm doing any shortcuts because we always do, and I keep saying this, you always do Lewis dot structures the same way. Don't take shortcuts. Count the number of valence electrons before you do anything else. There's 6 in this, plus 4 times 7 in this, so that's 34 electrons we need. Now, the next step, doesn't matter what order you do these 2 steps in because you're going to have to do this anyway. Put your central atom in the middle, attach with single bonds all your peripheral atoms, and then add the lone pairs to get everybody 8 electrons. How many electrons are represented in this arrangement? 32 electrons, but we need 34, so we've got to put 2 more electrons on. Where?
T.
You've got to put it on the TE. Always put the extra electrons you need to add onto the central atom. Now where? Where in the world? Just put them in somewhere.
Yeah.
What's the coordination number then at the TE? 5. Still 5. It's got 4 atoms attached plus 1 lone pair. So that means that it's going to have this separation of orbitals. Now which atoms should be taken off? Should one of the above or below atoms be taken off or one around the waistline?
Waistline.
It is the waistline, yeah. So it's going to look like this.
Why did you say waistline?
It's around the middle. Okay. So what is the shape of this? What would you call this shape?
Take away
It is technically a pyramid. So.
Pyramid.
No, it's like there's a
Pyramid without one of the edges. All right, so I can just imagine these chemists, these professors, thinking about their grandchildren. And what they called this thing, they call it a teeter-totter.
Seesaw.
A seesaw. Right. That is what we call it, is a seesaw shape. Can you see the teeter-totter in here?
Such a weird
Yeah.
More shapes.
They go from these fancy trigonal bipyramid to seesaw.
Mr. Moore, that was a serious question there. Why'd you take it off?
Oh, I thought you were asking me why I was calling it the waistline.
No, that was serious.
To maximize the difference. If something needs to spread out for whatever reason, it's that one that's got more room to spread out. It's not really true, I guess, is it?
It's got like 100.
Well, yeah, it's got, right, yep. All the other angles around the top and bottom ones are 90 degrees, where this one can spread out a little bit more because it's got 120 degrees around it. I think that's more spread out. So, the shape on this thing is officially known as the seesaw shape. And as I was talking about before with the lone pairs kind of spread themselves out, putting the squeeze on the remaining angles. So what are the remaining angles? I am going to say, you know how before we were estimating about a 2-degree decrease in the angles. I'm not going to go that far. Now that there's a little bit more crowded around there, I'm not going to say we lose a full 2 degrees, but I will say this. The angles are less than 90 and less than 120 degrees. I don't know what the angles are, but I propose that they're less than what they were when that was not a lone pair. Brooke?
Would they ask us the seesaw shape on the AP? Like, would they ask us to classify atom as a seesaw?
They have said that they won't, but I don't trust them. That's why you're learning this.
They don't know the quiz and that time.
Will the quiz
Will the quiz for you ask?
Will you ask?
Yes, I might. Yep,
Oh.
I might.
Wait, what? Do you ask for the angles too?
Yes.
Wait, which part's the seesaw again?
Wait.
Can you show?
Yeah. So you've got 120 degrees or so there, and then 90 degrees to those. So here's our seesaw. Those two that are 120 degrees act as the base of the teeter-totter. 90 and 120.
Thank you.
There's a model of a seesaw shape too, and that's just like what you see here. Trigonal Bipyramid. Okay, so between, you got these up and down, right? From there to there is 90 degrees.
Oh, and then from in between.
This is a plane that's perpendicular to that line. And then these between one another are 120. Like that, okay? Any other questions about this? It's 10:17. Let's do at least one more. I'm going to give you another lone pair. How are you feeling about Lewis dot structures? Do you want to continue doing them together, or can I just do them quickly?
Together.
Quick wait.
We'll do this one together. So the next one that I have is ICl3, iodine trichloride. Count the number of electrons, 7 plus 2. No. 3 times 7. Should give us 28 electrons. Okay, so put the I in the middle, that's the least electronegative. And 3 chlorines. Add the lone pairs. And the iodine is going to need a lone pair on it because it didn't have 8 electrons, or it only had 6 with the bond, so it needs another. How many electrons do we have here? 8, 16, 24, 26. Oh, I need 28. So I need another lone pair on the I. Yeah? So how do I arrange that? I'm just going to erase that one that I had before and make some room for the next lone pair, like that. The iodine has 2 lone pairs on it. Do you see a coordination number of 5 on the I? It's 5. A total of 5. You got 3 bonds and then 3 bonded atoms and 2 lone pairs for a total of 5 things. So when you have a coordination number of 5, you get this trigonal bipyramid arrangement. But we need to take 2 atoms off now and have 2 of them missing. They're both going to come off the waistline. Now what's the shape?
Triangle.
What, Michelle?
T.
It's a T shape. It makes the shape of a T. T shaped. Yeah. Not TEA, just T.
I was hoping we would have tea party here.
You what?
I was hoping we would have a tea party here.
In honor of the T shape? It's a great idea.
I don't know, just like took something out of your somewhere.
There it is. There's our T shape. It's flopped over. Oops. But yeah, this is a T shape. Okay, my friends, what is the angle of that T? Lone pair here and a lone pair here.
90.
Is it 90 or is it less than 90?
Less than 90.
Maybe just a little bit less than 90.
86-ish.
Nah, just under 90.
89.7.
I don't know. We're just going to say less than 90.
We need like a lower bound also. Because the lone pairs and all electrons.
Time.
We'll continue this tomorrow. That'll be the first one. It's good? It's good. Okay, so yeah, we'll work on that tomorrow.
See, the thing is,